Okay, let's do an analysis where we are going to experience a bifurcation. So suppose we let k equals 0.1 and c equals 4 be fixed values for the population. We want to introduce fishing at a rate of f fish per month. Update dy dt to take into account this flow rate. So dy dt as it stands is going to be 0.1y times 1 minus y over 4. Now I'm going to incorporate an independent term which is going to account for fishing at a rate of f fish per month. Assuming t is in months, and that means that this would already be in fish per month. And so if I wanted to take away f fish per month, if that's now going to represent a brand new outflow term, right? So here's our population. There's already some natural birth and death cycles given by this logistic model itself, but now I'm also going to have a independent extra drain in this tub at a rate of f fish per month. Now I want to understand how this parameter affects the population. When am I going to begin overfishing? Because at some point you can imagine that even with a big enough population size, if you fish too much, then you're actually going to cause dy dt to always be negative. Let's conduct an analysis. Suppose that y is in thousands of fish. Create a bifurcation diagram for f is between 0.05 and 0.08 in increments of 0.01. What do you notice? Is there a bifurcation value somewhere? Can you guess what it is? So let's start off with f equals 0.05. So I'm going to draw a phase line for that, and all I'm going to do is I'm just going to come over to Wolfram Alpha to help me with this analysis. I'm going to plot this function and look at different values of f. So here I'll change this to 4, and here I will do minus f, and of course f is not a known symbol, so Desmos wants to insert a slider, and we're completely fine with that. Let's just change our slider to go from 0.05 to 0.08 in steps of 0.01. Okay, there we go. We'll click done, and now we'll move this over here. So if we let 0.05 thousand or 50 fish be caught each month, then that suggests that we'll have two equilibrium points, 0.586 and 3.414. Now recall that if f was 0, we had equilibrium points of 0 and 4. Okay, but oops, I just changed that, 0.05. Okay, but now notice what happened. When I'm starting to fish, I've really closed that interval on which the population has opportunity to grow. So my carrying capacity, even though it's 4, the maximum number of fish my population can support is only 3.4. And that should make sense because we're fishing a bunch of them out of there. Right now, you might say, well, why is it 0.05? Why didn't we subtract 0.05? Well, it's a little bit more complicated than that because this is a monthly fishing rate, which then naturally affects reproduction, right? Because those fish that we catch can't reproduce, and so it affects more fish than we might imagine. Also, if you have fewer than 0.586 thousand or 586 fish, then your population is going to go into extinction if you're going to fish at that rate. So we'll just say about 0.586 and 3.414. 0.586 and 3.414. Okay, so I'll draw here y equals 0.586 and y equals 3.414, and the population wants to grow on this interval. So still, this acts as the kind of updated carrying capacity, and we'll have the population wants to approach that steady state, and if you ever have fewer than 0.586 fish, the population will go into extinction. So if you wanted to allow this kind of fishing, you'd want to make sure that you started off with at least somewhere around 600 fish instead of 586 or below. Now if I increase this parameter just slightly and make it 0.06, let's see what happens to the equilibrium points now. And I can just come over here and drag this slider to make it 0.06. And now let's see what happens. So now my equilibrium point, oh, look at that. So now I have to have at least 735 fish, because if I have fewer than that, my dy dt will be negative, and that means that my population will go into extinction. And now that I'm fishing more, my carrying capacity has been decreased sizably. 0.735, 3.265. And 3.265. So those have just come together. And once again, the behavior surrounding them has not changed. So that means there's no bifurcation that's occurred as a result of me changing that parameter. And now if I go to f equals 0.07, which I will do here, and just drag this to 0.07, once again, those equilibrium points have squished in even further, and now I have an even smaller window of growth, 0.9 and about 3.1. So here we are at about y equals 0.9 and y equals 3.1. Again, tiny window of growth here in comparison to what we had with less fishing. But notice that again, the quality of those equilibrium points, still one is a sink and the other is a source. And finally, if I look at f equals 0.08, let's see what happens here. If f equals 0.08, those equilibrium points have moved in even closer, 1.106 and 2.894. 1.1, and we'll just say about 2.9. And again, same behavior, small window of growth. And if your population unfortunately drops below 1,100, at that fishing rate of 80 fish per month, they're not gonna make it. Now we want to look if there's a bifurcation value. Now one of the things I see is that eventually these two equilibrium points will squish together based on what's going on here. So let's change this to something a little bit higher. Instead of 0.08, let's go up to 0.12 and see how that changes things. Okay, there's 0.09. Oh, wait a minute, what happened here? If f is 0.1, now I'm not going to draw this, this phase line for f equals 0.09. When f is equal to 1, I only have one equilibrium point, and that equilibrium point occurs at y equals 2. So at y equals 2, now I have one equilibrium point, and notice that to the left of y equals 2, dy dt is negative. Our graph is below the horizontal axis. It is a negative vertical value. And when y is bigger than 2, dy dt is also negative. So notice that now not only do I have just one equilibrium point, but that equilibrium point is neither a sink nor a source. It is now a node. So f equals 1 is the bifurcation. That's the bifurcation point at f equals 1. If f becomes bigger than that, look what happens. And we can kind of see what this parameter is physically doing to the graph. It's really just shifting it down. It's shifting the whole parabola down. And if I make it any bigger than 0.1, oh, I'm sorry, this should be 0.1, not 1. It should be a 0.1 right there. Then the population will go into extinction. Notice that I have no equilibrium points anymore. So f equals 0.1 was sort of that one indication, or that one point where we went from having two equilibrium points to having one equilibrium point. And by our definition of bifurcation, we have satisfied it. Now, hunting for these is not always trivial. One of the things we can do is just play around with the value in something like Desmos, and we can find it that way. Another thing I can do is we know that really this parabola will, once the vertex shifts down, which started out at let's see, I make this 0. When we weren't fishing at all, notice that 0.1 was the was the value of the vertex, or the output value of the vertex. So if I shift this thing down 0.1 units, well, that's going to bring the vertex down 0.1 units, and that's where we're going to have the bifurcation value. So you can find this mathematically as well. If you kind of get real clever with the algebra and, okay, what transformation are we performing by subtracting this parameter off, then you can solve for this bifurcation value mathematically. The way we did it was just by experimenting and seeing, geez, if I make this value bigger, it looks like eventually these two equilibrium points may merge into one. And once again, what you'll see in a bifurcation plot is you'll see somebody actually connecting these points. This is going to be really sloppy, but it'll kind of look something like this, so that you can sort of see that anytime you're within the confines of this curve, that's where you have that small window of growth, and when you're outside of this almost like horizontal parabola, then you have pockets of decay. So that's really the holistic story of doing this equilibrium analysis. It leads to more powerful analyses which can start off or spawn this bifurcation analysis. And we've already done this with solving with the parameter intact. So we could solve this differential equation with f in there and then have a solution that involves f, and then experiment with the actual solution curve. But notice that we didn't need to do that. We did a bunch of different analyses without ever solving the equation.